Welcome everyone to this morning's Compass talk. It's a pleasure to introduce Maofeng Liu. Maofeng, actually he arrived here about a year ago, a little less than a year ago. I think he actually arrived on the day that the university closed down due to COVID. So that and he actually is, working remote like most of us. And he has an office somewhere in the MSc building, but even I'm not quite sure where. So Maofeng, actually his undergraduate degree is in hydraulic engineering. He got a bachelor's and a master's degree in a bachelor's in hydraulic engineering from Tsinghua University in Beijing, and a master's in natural science from the Chinese Academy of Sciences, also in Beijing. And then he came to the US and got his PhD at Princeton University in civil and environmental engineering, where he studied rainfall associated with the transition of tropical cyclones. Then he remained at Princeton for a couple of years as a postdoc, research associate, and then joined us here at Miami, as I mentioned, a little less than a year ago. And Maofeng does research, as you might guess, on the hydrological cycle, but on a range of aspects, everything from precipitation to tropical cyclones, to climate change, to the combination of all of the above. And this morning, Maofeng is going to talk about some interesting results he's found that show how the intensification of the hydrological cycle in a warming climate modulates the ocean heat uptake by through changes in salinity, which is turns out to be actually an important and previously undocumented process in modulating the transient climate change. And with that, I'll turn things over to Maofeng.
Hi, let me first share my screen. Okay, can everyone see my screen? Okay.
Yeah, we can see it.
Yeah. Okay. Great. Hi. Brian, thanks for the nice introduction. I'm glad to have this opportunity to introduce my work. So first, today is the first day of a new year in terms of the lunar calendar. So happy Lunar New Year. So in this talk, I want to talk about my recent work I've been doing for the last couple of months. I want to thank Brian and Boston in my group, and also Gabe and Wenchang from Princeton University for their contributions to this work. It really focuses on the transient climate sensitivity, which we know is tied to the rate of the ocean heat uptake. We will try to understand how the change in the global hydrological cycle impacts the ocean heat uptake, and then the transient climate sensitivity. Let's start with global warming. Important evidence of global warming is the ocean keeps warming up, and you can find it out if you just take a look at the observational records of the ocean heat content. And because the atmosphere and the land have a much lower heat capacity than the ocean, so over 90% of the top of atmosphere energy imbalance is actually stored in the ocean. And compared to the sea surface temperature, the ocean heat content seems to have a lower interannual variability and may better represent the signal of climate warming. And as shown in a recent study by Chen and al., both observation-based data sets and the climate model simulations suggest a growing ocean heat content over the past 6 decades. And this upward trend becomes larger in the second half 30 years than the first half 30 years, which indicates that the ocean warming is somewhat accelerating. But on the other hand, the ocean is warmed from surface downward. And because of this upper level warming, you would naturally expect the ocean to become more stabilized, because along with the with the warming, you will get a reduced ocean density. And this suggests this gas is approved by a recent study looking at the ocean stratification over the last couple of decades. And they analyzed a few available observational data sets and found that the stratification from the sea surface to the depths of 2,000 meters show a relatively robust increase, as you can see from the line here. And this increase is mainly attributed to the ocean warming. And because increased thermal stratification tends to reduce the efficiency of ocean heat uptake, their question comes up, how does the ocean warmed from above, which stabilizes, produce the observed ocean heat uptake? In this talk, we will try to come up with some mechanism that can help us at least partially address this question. So here we look at the hydrological cycle. And climate warming, a very important and a robust change is the intensification of global hydrological cycle. That is, the wet gets wetter while the dry gets drier. And this may not be true of inland regions, but holds quite well of oceans, which means that the change is strongly tied to the mean state. And this theory is well discussed in an influential paper by Isaac and Brian in 2006. And this intensification in hydrological cycle has many important implications. One of them is the amplification of the sea surface salinity pattern. That is, salty gets saltier, while fresh gets fresher. There have been a couple of studies on this subject in recent decades. For example, the one by Durack and al. In 2012. Actually, the observation of precipitation and evaporation is not quite reliable because of the large uncertainty. People actually use salinity observations as a more reliable proxy to explore the change in global hydrologic cycle. And if you take a look at the trend of sea surface salinity over the past few decades from the observational records, there's quite clear signal of sea surface salinification in the Atlantic and some parts of the Eastern South Pacific, and also some areas of the South Indian Ocean. And these are the places where the surface salinity climatology already maintains at high levels. So it sounds reasonable to hypothesize that the salinification can at least partially offset the temperature-induced ocean stratification. So it may play an important role in enhancing the rate of ocean heat uptake, and which provides a possible mechanism for understanding the accelerated increase of ocean heat content. So to demonstrate this hypothesis, we set up a series of climate model experiments using a JFDL climate model called FLOR. We first conducted a so-called standard simulation, including a control run, which keeps the radiative forcing and other conditions to the level of year 1990, and also a transient double CO2 run by increasing the CO2 concentration 1% per year until doubling. And after that, we keep the CO2 concentration as doubled. And this type of CO2 experiment is one of the simulations performed by the CMAPS community to understand how increased CO2 forcing impacts the climate by looking at the difference between the CO2 and the control simulation. And the standard simulation, or we can call STD simulation, serves as a baseline. And we also conducted another 3 sets of perturbation simulations. The only difference from the STD simulation is that we fixed the sea surface salinity to the seasonally varying climatology simulated from the STD control run. So the idea is to not allow the sea surface salinity to respond to the changes in global hydrologic cycle and the CO2 forcing. So if we compare the perturbation experiments with the STD run, we can kind of separate the impact of ocean salinity changes due to the CO2 forcing. In the first perturbation experiment, we fixed the sea surface salinity over the global scale and call it fixed salinity GL. And we also have 2 other perturbation experiments in which we just partially fixed the sea surface salinity. And later in this talk, I will get to why we need these 2 experiments. And to focus on the transient climate sensitivity for the CO2 run, we use the 20-year simulations centered on the year the CO2 is first doubled. While for the control run, we use the 100 model years. The difference between them represent the model response to the CO2 forcing. Before we go ahead to look at the climate response to CO2 forcing, I want to first mention that fixing sea surface salinity itself had a relatively small impact on the control runs, at least for things we care about. For example, the surface temperature. The difference in surface temperature between the fixed salinity run and STD run shows some variation of the 100-year simulation, but is relatively small. And on average, the difference is on the order of like 1/1000th of the surface temperature increase in response to CO2 forcing. So given this result, we don't need to worry too much about the impact of fixing salinity, surface salinity itself on the control run. Now, let's look at how the global hydrocycle responds to CO2 forcing in the floor model. The top figure shows the spatial pattern of the precipitation minus evaporation from the 100-year control run, or we can call P minus E. P minus E indicates positive P minus E indicates wet conditions, which is shown in green color, many located in tropics and high latitudes, while negative P minus E indicates dry conditions, as shown with the brown color, and many in the subtropics. The bottom figure shows the response of P minus E pattern to the CO2 forcing. And we can see that in general, dry gets drier while the wet gets wetter. Specifically, the two red circles highlight the substantial drying in the subtropical Eastern South Pacific and also the tropical and subtropical Atlantic, suggesting the intensification of the global hydrocycle and CO2-induced warming. These results are consistent with previous research work. Then, in response to this intensified hydrocycle, we see an amplified pattern of sea surface salinity. This figure shows the difference in the response of sea surface salinity to the CO2 forcing between the STD and the fixed salinity run. I should mention that for the latter, the sea surface salinity has no change from the control run to the CO2 run because we fixed the salinity. So the difference mainly comes from the STD simulation, which is driven by the hydrological cycle change. As marked by the red circles, the subtropical Eastern South Pacific and also the tropical and subtropical Atlantic, which becomes drier, as mentioned in the previous slide, show a clear signal of surface salinification, as indicated by the red color. We can also see some salinification over parts of the South Indian Ocean. And this sea surface salinification driven by the global hydrocycle change is expected to increase the surface density and then reduce the ocean stratification, and which would then tend to increase the ocean heat uptake. Now let's quantify how much ocean heat uptake this surface salinification can drive. The figure in the top row shows the difference in the response of ocean heat content to the CO2 forcing between the STD and the perturbation experiment. Following the ocean salinification, we clearly see a greater ocean warming in the STD simulation, as shown here. And as indicated by the increase of ocean heat content, and which is true over both Atlantic and the non-Atlantic oceans. And this greater warming is not depth universal, but is rather dominated by ocean depths greater than 300 meters. For the near surface level up to 300 meters, as shown here, we actually see less heating in the STD run compared to the fixed salinity run. An important implication of this is less increase of sea surface temperature in the STD run. So compared to the fixed salinity run, the STD run produces a greater ocean warming, and this heat is stored in the deeper ocean, while the near surface level shows less warming. And this kind of distribution of vertical heating is clearly represented in the right subfigures, which shows the difference in the response of zonally integrated subsurface temperature to CO2 forcing. And by the way, the salinity is shown in a similar way, but in the figure on the left. So from the temperature figure, we can clearly see a less temperature increase in the upper ocean, while a greater temperature increase in the deep ocean in the STD ROM compared to the fixed salinity ROM. So the next question is, what drives this vertical difference in heating between the two ROMs? We checked the mixed layer depths, but there's no significant difference between the two experiments. So the wind-driven upper ocean mixing seems not a big player in accounting for the response difference between the two types of experiments. And the red circles highlight the impact of salinification on ocean heat uptake. And you can see that the greatest heat anomaly will correspond with the largest salinity anomaly for both Atlantic and non-Atlantic oceans. But this is just part of the story. The ocean salinification leads to reduced ocean stratification, which further leads to upper ocean cooling and deeper ocean warming. And cooling indicates denser water, while warming indicates lighter. So this difference in the vertical heating can actually further reduce the ocean stratification, which kind of forms a positive feedback, kind of amplifying the impact of the surface salinification. The figure on the left shows the difference in the response of ocean density to the CO2 forcing between the STD and the fixed salinity ROM, and which is similar to the subsurface temperature and salinity we just showed. And it is also presented in the form of zonal integral. So the y-axis is a depth, while the x-axis is a latitude. The Atlantic is shown on the left, while the non-Atlantic oceans are on the right. So the top row shows the density, while the second row shows the contribution to density from the salinity, while the bottom row shows the contribution from the temperature. And you can see that this kind of difference in density in the top row would indicate reduced stratification in the STD ROM than the fixed salinity ROM. And you can see that the contribution from the temperature is kind of important player in driving the density difference. So not only the surface salinity itself can cause reduced stratification, the resultant vertical structure of the temperature change provides also important positive feedback to further reduce the stratification and thus enhance the ocean heat uptake. Compared to the fixed salinity ROM, the STD simulation produces a greater increase of ocean heat content in response to the CO2 forcing, as shown in the red lines in the left figure. And correspondingly, the STD simulation produces a less increase in surface temperature, as shown on the right in the right figure. And if you look at the transient climate response, or TCR, which is defined as the global surface temperature change at the time of CO2 doubling in a model experiment with a 1% per year CO2 increase. TCR is often used as a standard metric in the community to indicate the model sensitivity to the CO2 forcing. And here in the floor model, the TCR difference between these two types of experiments, which 0.4 K. To give you some sense how much this is, the standard deviation of TCR from the CMAP6 climate models is also 0.4 K. So it is not something trivial, what we see in our experiments, but something we need to keep in mind when we think about how much warming we can get and the greenhouse gas forcing. So the experiments we conducted are useful in separating the impact of hydrological cycle change induced ocean salinity on the ocean heat uptake and also transient climate response. But there's one problem here. We noticed that the STD simulation shows more cooling than the fixed salinity simulation of the entire water column in the subpolar Atlantic. And this may be related to their difference in the Amok, which is Atlantic Meridional Overturning circulation. Amok is a very important component of the ocean circulation, as we all know. The figure on the left is a plan view to give you some idea what Amok is. So the brown arrow shows the south to north movement, which occurs in the upper ocean and which transports warm salty water from the subtropics to subpolar region. And water in the subpolar gets cold and sinks and forming the so-called North Atlantic deep water, and then moves back to south, as indicated by the blue arrow. People have found that in global warming, the strength of Amok tends to decrease, partly because, for example, the Arctic ice melting can provide more fresh water into the ocean. And also, on the other hand, the change in the P-C pattern in response to CO2 forcing can also cause subpolar freshening, as shown in the figure on the right, which makes it more difficult for the deep water formation because of the increased ocean stratification. And this could reduce the strength of the circulation. Compared to the fixed salinity experiment, the SGD run has more subpolar freshening because of the change in the P-C as more fresh water, as indicated by the red circle in the figure on the right. So we can expect there's a greater Amok weakening in the SGD experiment in response to the CO2-induced warming. We can check this by looking at the so-called stream function. So the stream function is defined as the integral of the oceanic meridional velocity from surface to some predefined depths, and also from the western boundary to the eastern boundary of the Atlantic for some predefined latitude. And here we focus on the stream function at 40 degrees north, and we can see that both the SGD and both SGD run and the fixed salinity run show a weakened Amok and the CO2 forcing. As you can see from the solid lines to the dashed lines. The SGD run, as indicated by the red lines, shows a greater weakening of Amok. And this difference in Amok weakening between the two experiments can lead to difference in ocean heat uptake. So the ocean heat uptake difference between the SGD run and the fixed salinity run that we have been showing, that we have just shown, may be a compounded effect of both Amok and also the surface salinification. So to reduce the impact of Amok, we set up two other perturbation experiments with partially fixed sea surface salinity. As shown in the two figures, the oceans with fixed salinity is masked with orange color. So the idea is to not fix the salinity in the subpolar Atlantic and Arctic region, as indicated by the red circle, which is to eliminate the impact of P-C change. And then we kind of expect they can get a closer Amok weakening with STD simulation. And another benefit of the partial salinity fixing is to allow a better understanding of regional signification on ocean heat uptake and also the surface warming. So for the figure on the left, we focus on the subtropical Atlantic salinity fixing, while for the figure on the right, we focus on the non-Atlantic oceans. And as we expected, the two partially fixed salinity simulations, as indicated by the green and also brown lines, shows a closer Amok weakening to the STD simulation, which is shown by the red lines, by the way. And then for the simulation with fixed salinity and the subtropical Atlantic, we still see a pronounced heat anomaly associated with salinity anomaly, as highlighted by the red circles. Similarly, this coupling between the heat anomaly and the salinity anomaly is also seen in the simulation with fixed salinity in the non-Atlantic oceans. So after considering the impact of Amok, we can still see the important role of the sea surface salinification in driving the ocean heat uptake. Here I want to mention that something that is quite unexpected. So for the case that we only fixing the subtropical Atlantic salinity, surprisingly, we see increased salinity in the non-Atlantic oceans, as shown here, and correspondingly, which drives more ocean heat uptake into the deeper ocean. And in the case only fixing the non-Atlantic salinity, we see a similar scene. That is, the Atlantic Ocean shows some sort of like salinification, and which drives more ocean heat uptake. So this result suggests that the impact of the surface salinification is not just local. There's some kind of remote effect. We did some further investigation. The result is not shown here, but we found that the salinification over remote oceans actually comes from the change in the P-C pattern. Our current guess is that the surface salinification leads to more ocean heat uptake and then less surface warming. And this change in surface warming can reduce the atmospheric convection and then precipitation. So the decrease in rainfall can then lead to more salinification over remote oceans. So more analysis are needed to further explore this aspect. But the bottom line here is the fixed salinity experiment on the global scale may actually underestimate the impact of the ocean salinification because it does not allow this remote effect in the experiment. For summary of this presentation, we argue that the intensification of the global hydrologic cycle and the CO2 forcing would lead to an amplified pattern of sea surface salinity, resulting in ocean salinification, especially in the subtropical Eastern South Pacific and tropical and subtropical Atlantic. We suggest this salinification plays an important role in offsetting the increased thermal stratification by enhancing the ocean heat uptake with near surface cooling while the deep ocean warming. And this kind of vertical structure of subsurface temperature change can further reduce the ocean stratification, forming a kind of like a positive feedback. And along with the change in the ocean heat uptake, we would expect get a lower TCR or transient climate response. And as in the floor model shown, this change in TCR is close to the standard deviation of the TCR from a bunch of CMAP climate model simulations. So this is all I want to talk about today. Thank you. Any questions are welcome.
What's going on? Is it over already? I had a phone call. I couldn't follow you in the last minutes.
That's fine. That's fine.
Hello?
Hi.
Is the seminar over?
Yeah.
So we can ask for questions. If someone has a question, please activate your microphone and camera and speak. Maybe we have no questions.
Yeah, I have one question here.
Yes. Can we see you?
Yes. It's yeah, nice talk. Thank you. I was wondering if there's any feedback associated with the advection of salinity interbasing from other bases, for example, from the Indian Ocean to the Atlantic, and things like that. That would be a positive feedback on this increasing salinity in the tropics. Yeah, if you you think that could be something that that the ocean circulation would increase this effect, not only the effect of stratification?
Yeah. So yeah, so what we have done, we only consider like the input from the permanency pattern. We don't go very deep into looking at the advection of the signification. Yeah, yes, as you just said, if there's like a positive advection which can drive which can change the ocean stratification of other places. The only thing we look at is the Amok, which is an important part of the advection in the Atlantic Ocean. Yeah.
Right. And just another quick question: why did you use 40 north instead of 26 north or something like that?
That's a good one. Actually, I just I don't thought too much about it. I just randomly use that one. And I think there's another another latitude people often use is like 26.5. That's where people, I think, put a lot of observations there. So that's a latitude people often use. Yeah, I think we can take a look at that. But I think that won't change much on the result of the Amok weakening between these experiments. Yeah.
Okay.
Any further questions or comments? Maybe not. Somehow we didn't have a lot of people in the audience today, maybe because you are not so well known in our community so far, but maybe people can watch the video and then you become famous with the video. So if that's all, thank you, Maofeng, for the presentation. Unfortunately, I had a phone call in the last few minutes, so I missed the end, but I will watch it again on video. There will be no seminar next week, but in 2 weeks, so please watch the emails to see what will be our next seminar. Thank you all for coming and have a nice weekend.